Hey guys. So in the last video, I went through the kind of calculus formal definition of impulse and momentum. In this video, what I want to do is kind of pull them apart and talk to you about how to interpret them or how to think of them in different ways. And a lot of this is just going to go back to your knowledge of calculus and math, but it's sort of helpful to pull it out in different ways. All right. So last time we found that impulse, J, is the integral, and you're integrating over time, from some initial time, so T initial to T final. You integrate over whatever time interval that the force acts. And it's force, so that tells you that force is a vector, excuse me, and you're integrating the force over time, therefore the impulse is also going to be a vector. Okay, now how can you think about this? And maybe a good way to start is to simply imagine that we had a block. Imagine there's no friction. There's really only going to be one force acting on it. So let's go ahead and draw that here. And we're going to, this is going to be our system. And we're going to have, I don't know, I suppose it could be your finger pushing on it. Okay. And there are many ways you might imagine pushing on it. One way might be a constant force. Okay, so another way might be that you kind of poke it. So it would be no force, and then a spike, and then no force. Both of those are possible ways to interact with this block. And the benefit of this example is because the force only acts in one direction, yes, all right, it is a vector quantity, but as we did way back in kinematics, in 1D, you can graphically, you can really handle a lot of this stuff graphically. And so let's do that. So let's imagine that we were to graph the force applied as a function of time. And there are many ways you might imagine doing this. So let's imagine I kind of start small, push it, and then let go. So the force would start small, it would peak, and then it would go down. Okay. At this point, we can use all of our knowledge of calculus to help us interpret what impulse means. Impulse is the integral of force over time. Here I have a graph of force over time. Visually, we know, or geometrically, we know that the interpretation, or an interpretation of an integral is as the area under a curve. So what we find here is if you were to shade in not a position versus time graph, but instead if you were to shade in a force versus time graph, you would learn that the area equals impulse. Okay, the area under a force graph versus force versus time gives you the impulse. Another thing, mentally, I can either give it a fancy name or just kind of make this wave my hands, but you could also imagine that to calculate this area, you might imagine that you kind of estimate the average force, which would be something like this maybe, over time. And you can imagine that there is a rectangle which has the same area as the true graph, but it's just a flat function. Well, we would say then that this is so the force was there, and this would be the average force. So another interpretation of impulse is that the impulse equals the average force times the time over which the force acts. So even if the true force has sort of a complicated form, if you know how long it interacts, you can actually maybe estimate an average value of the force and calculate the impulse from that. So, okay, so those are a couple ways to think about impulse. This comes out of the mean value theorem in calculus, where you say that if I have a function that what you have then is the integral of any function, say over dx, equals delta x times the average value. Okay, so that's something you should have learned. I should have been Calc 1, I would believe, but even if you didn't, it's sort of graphically clear. So you don't really need to know that as a math theorem, just it's visually clear that you could sort of choose an intermediate sort of typical or average value of the force. And if you choose the height just right, the area in the rectangle would exactly reproduce the area in the curve, and that allows you then to interpret the impulse as the average force applied over the time interval. Very good. Let's do an example now and see kind of how you can use this to and the concept of momentum to calculate the change in motion for an object. So our theorem is called the impulse momentum theorem. States that the change in momentum equals the impulse, and it would be the net impulse. So you'd have to find the impulse from every individual force, and you add them up. Okay, so that's our theorem, and we're going to use that to describe the motion of a block, the same block actually. So here's our picture. I'll put the picture over here. So I have a surface. Let's just imagine that there is no friction. And we're going to exert a force on it. And I'm going to go ahead and assume that the block has a mass of 2 kilograms. And I'm going to assume that at the beginning, the block isn't moving. So we'll say that V initial is 0 meters per second. And finally, we're going to assume that the hand applies a force equal to, let's just make up a number. Let's say that the force from the hand equals, I don't know, 5 newtons. Okay. Now, there are a couple ways we could go from here. Let's first just imagine that we know the time interval. So let's say we apply a force over a time interval of 3 seconds. And then let's turn it around and then let's use the impulse momentum theorem to calculate what is the final velocity of the block. So here's my theorem. The theorem says the change in momentum equals the net impulse. And there's nothing happening in the vertical direction, so I don't even worry about it. The only thing of interest is the horizontal direction, and that lets me say, okay, so the change in momentum will only be in the horizontal direction, in which case the only force giving any impulse is the hand, or any relevant impulse. So I can just plug in, right? So when I start one of these problems with impulse and momentum, the place where I start is first define my system. It's the block. After I do that, I write down delta P equals J. That's it. It's kind of like in a force problem where you start by drawing a free body diagram. For a conservation law problem, I start by defining the system, and then I immediately write down the conservation law of interest. And then I kind of unpack, what do these symbols mean in this context? But it always starts exactly the same place. And I'll give you a hint, on any sort of test, that's going to buy you some partial credit. Because it's always the same, and it's important that you just do it. Very good. Change in momentum equals net impulse. So let's write this down. The mass never changes. So I can write the change in momentum as mass times change in velocity. Remember, we're trying to find V final. I said it out loud, I think, but should have spelled it out. Trying to find the change in momentum, or sorry, change in velocity. Here's my formula, or for mass times velocity, and that equals J net. So that's going to be the impulse. I can write it, no, okay. The force is constant, so we're going to apply it over 3 seconds, because delta T is 3 seconds. And the force of the hand, dt. Now, it's kind of a big hammer for a small peanut because it's a constant force, and I just know that this integral is going to evaluate to the force of the hand times delta t, which is 3 seconds. On the left-hand side, I have the mass, and I just unwind what these symbols might mean. So that tells me V final minus V initial. And then I rearrange it and find that V final equals V initial plus force of the hand over M times delta T. We can plug in numbers. So we get 0 plus 5 divided by 2 times delta T, which would be 3. So that's 15 over 2, it's 7.5. Okay, awesome. You might be thinking, wait a minute. We had an equation kind of like this before, relating changes in velocity, changes in time, and oh wait, but if you have a constant force, then the force over mass is nothing other than acceleration. In fact, for constant forces, this simply gives you what we call kinematic equation 1. Ta-da! It's no surprise, right? We started with Newton's laws. We use them to derive impulse and momentum. So that means that really anything we can solve with impulse and momentum, it has to be compatible with Newton's laws. It's just that for some problems, it's much easier to use impulse and momentum. That's really the main payoff of that one. All right, let's do another example. Let's say, rather than having a constant force, let's assume I had a variable force. Let's assume that my force, excuse me, from my hand starts small, peaks, and then goes back to 0. And I'm going to give you the information graphically. So let's assume that the force from my hand follows the following curve. Okay, and I'm going to go ahead and assume that the peak value is at 10 newtons, and I'm going to assume that the central value, the value of the peak, is at time equals actually, I don't even need to give you that, do I? I really just need to give you the time where it's all done. So let's say that was 3 seconds. Okay. And assume the same mass and same initial velocity. So we worked the problem more or less in the same way, except that now when we have to evaluate the impulse, I'm trying to cover up the shadow, sorry, the reflection, I apologize. It's just what it is. We're trying to, no, it doesn't matter. We need to evaluate this integral. And to do that here, it's really easier to go back and just do this bit graphically. Right? Just calculate the area. So we go back and we use our area formula for a triangle. Remember that says the area of a triangle is 1/2 the base times the height, which in this case, the base is going to be 3 seconds and the height is going to be 10 newtons. So this is 1/2 10 newtons times 3 seconds. So that's simply going to be 15 Newton seconds. It's the same as a kilogram meter per second. Okay. So that is our impulse, 1/2 the base times the height. Okay, so we can go back and evaluate our formula, and we would say the mass times V final minus V initial equals 15 kilogram meter per second. And then I can rearrange this and solve for V final equals, it's going to be 15 divided by 2, it's going to be 7.5 meters per second. In fact, you can get the same effective change in momentum because it turns out if the peak value is 10 and the width, the base of the triangle is 3, then in fact the average value of the force is 5, just as in the previous example. So this is a different, completely different force, but by adjusting the magnitude, and you can achieve the same final velocity. Okay. So those are 2 really simple examples of how you use the impulse and momentum theorem to calculate properties